Hello, sir. Welcome to the CSE425 Neural Network presentation. This is Anindra Majumdar, and my topic is the transformer model, a groundbreaking development in machine learning, particularly in the field of natural language processing. Since its introduction in 2017, it has revolutionized how tasks involving sequential data are approached. This presentation will cover the key aspects of the motivation behind the model, the philosophy underpinning its design, the architecture of the model, the attention mechanism at its core, the applications, the mathematical workings involved, and some of the limitations it faces. By the end, a comprehensive technical understanding of the transformer model should emerge. So the context in which the transformer model emerged is essential to understanding its impact. Before 2017, models such as recurrent neural network and long short-term memory (LSTMs) were dominant in handling tasks involving sequential data, particularly in language modeling. However, these models had significant limitations. RNN and LSTM struggle to capture long-range dependencies in sequence and become inefficient when dealing with longer sequences. A further limitations of this earlier architecture was their sequential nature, processing input step by step, making parallelization difficult and therefore slowing training, particularly with the large data. To address these issues, researchers from Google introduced the transformer model. In the paper, attention is all you need. By removing recurrence and bashing the model entirely on attention, the transformer dramatically improved the ability to capture long-range dependencies while enabling fully parallel computations. This marked a significant shift in machine learning, especially in natural language. Moving to the philosophical foundation of the transformer model, the key shift was away from the sequential step-by-step processing of the sequences. Instead, the transformer treats the entire sequence holistically, allowing each part to attend directly to every other part of the sequence. This marked a conceptual departure from the traditional methods of handling sequence data. The key principle is attention. Rather than focusing on one part of the sequence at a time, the transformer learns to attend to the most relevant parts of the input based on the task at hand. This ability to model relationships across the entire input in parallel found fundamentally. The key principle is attention. Rather than focusing on one part of the sequence at a time, the transformer learns to attend to the most relevant parts of the input based on the task at hand. This ability to model relationships across the entire input in parallel fundamentally improves the model's efficiency, effectiveness, especially when dealing with the longer sequences and complex relationships. So let's move into the architecture overview. The architecture of the transformer model is both elegant and effective. It comprises two main components, an encoder and a decoder. The encoder processes the input sequence and produces a set of representations, while the decoder takes these representations along with the target input to generate the output sequences. Each encoder and decoder block consists of two primary sublayers. The self-attention layer. This allows the model to assign varying levels of importance to different tokens within the sequence when encoding each token. And the feed-forward neural network. The sublayer further processes the learned representations. Residual connections and layer normalization are applied after each sublayer to stabilize training and ensure the gradients flow smoothly. Importantly, the transformer doesn't rely on the recurrence or convolutions, which were the hallmarks of the previous sequence models. Instead, it leverages the attention mechanism to capture relationships between tokens, enabling the model to process the entire sequence in parallel. The self-attention mechanism lies at the heart of the transformer science. But what exactly is the self-attention? Simply put, it is the process by which each token in the input sequence can attend to every other token. This allows the model to weigh the importance of other tokens when encoding a particular token, regardless of their distance from each other in the sequences. Each input token is transformed into three vectors: a query vector, a key vector, and a value vector. The query vector of each token is compared with the key vectors of all tokens by computing dot products. These dot products provide attention scores, which indicate how much attention one token should pay to another. After normalizing this scores with a softmax function, a weighted sum of the value vectors is taken producing the output. Self-attention gives the transformer a remarkably ability to model long-range dependencies, which was a key weakness in the previous architectures. The mechanism of self-attention module will cover in the mathematical notations part. Now, a brief look at the mathematics behind the self-attention mechanism. The process starts with the query, the key, and the value matrices, all derived from the input sequences. Q is the matrix of the query vectors, K is the matrix of key vectors, and V is the matrix of value vectors. But BK is represent the dimensionality of the key vectors. This dot product QKT results in the uh, attention scores determining how much focus should be placed on tokens. Dividing by square root of BK prevents a large value of the dot product, ensuring stable training. Finally, the softness function normalizes the scores, which are then used to compute a weighted sum of the value vectors. An extension of self-attention mechanism is multi-head attention. This mechanism allows the model to perform multiple self-attention operations in parallel, each with different linear transformation. By doing so, the model can capture various aspects of the relationships between tokens in sequence. After performing the attention operation, the results of all heads are concatenated and linearly transformed, providing a richer representation of the input. Additionally, since the self-attention mechanism itself doesn't retain any information about the order of tokens, positional encodings are added to the input embedded. These encodings are sinusoidal functions to encode the positions of each token, enable the model to account for token order in the sequence without relying on the recurrence. Let's jump into the uses and application. The transformer model has proven incredibly versatile, finding use in a wide range of applications, particularly in NLPs, more generally natural language processing and the vision tasks. One of the earliest success was in machine translation, was the model outperformed previous approaches. So the notable applications includes the bidirectional encoder representation from the transformers, shortly BERT, which has set the new benchmarks in the tasks like the question answering and the language understanding. And the next notable application is the generative pre-trained transformer, shortly GPT, which has excelled in trick generation tasks and in the backbone of many conventional AI models. And then, and lastly, T5 text to text transformer, which frames all NLP tasks as text generation problems. Outside of the natural language processing, the transformer has been adopted in image processing through vision transformers, even for biological applications like protein structures with AlphaFold. And not only that, the long sequence time series forecasting using Informer with the Informer model. So This kind of diverse applications made it extremely flexible to across the various machine learning fields. So let's jump into some limitations of this transformer model. Despite the widespread success, the transformer model is not without limitations. One significant challenge is the computational complexity. The self-attention mechanism has a time and space complexity of n squared b plus n d squared, where n is the length of the sequence, which is still much faster than RNN and the previous models and produces still better results, we know. Still, the quantity complexities make it difficult to scale the model to very long sequences. Efforts to overcome these limitations have led to models such as longformer and reformer, which introduce first attention mechanisms, reducing the computational load while maintaining much of the transformer's power. Another limitation is the vast amount of data and computational resources required for training. Pre-training models like GPT or BERT requires immense infrastructure, which is often out of reach for the smaller research teams or organizations. Lastly, although transformers are adept at the capturing relationships between the tokens, they may struggle with the fine-grained reasoning tasks without additional modifications. So, in summary, the transformer model represents a significant shift in how sequential data is processed by leveraging attention mechanisms and discarding recurrence. It pushed the boundaries of machine learning, and particularly in natural language processing and the vision researches. The versatility has led to the successful applications across a range of domains, from text processing to image recognition and the biological tasks. However, the model's computational complexity and resource requirement present ongoing challenges for research and development. Thank you for your time, and thanks for giving me an opportunity to present. So that's all from my side, and I'm concluding my presentation. Again, thank you so much.